Hello everyone. In this video, we are going to talk about ladder logic diagrams or ladder logic, which is the most common method for programming PLCs. We are going to look at different symbols and different terminologies, and then how we set up the logic in the system. And after that, we are moving to three examples from simple to mid-level to a little bit higher level. And these examples 1 and 2, or 2 and 3 actually, they are taken from this website, Instrumentation Tools, which is a really good website with lots of useful material for learning PLCs. So let's get started. So what is the ladder logic? It's a graphical language. You're gonna see we're gonna use symbols in place of sensors and actuators and timers and all the other electronics. And the goal of it is to replace the older relay circuits. So making it kind of easy to understand for technicians and the people who used to use relays for controlling systems and making control panels. So it's the most popular programming language, as I said, for PLCs, and we're gonna focus on that. Why do we want to focus on that? As I said, it's widely adopted. Any PLC has ladder logic, and it's really good for systems that have discrete controls. There are a few specific number of states the system can be in, like on, off, and stuff, or sequences and so on. So it's really good for that. If the system gets more and more complicated, it might not be sufficient, as I mentioned in my previous video, and that's where you can bring in other blocks and structured text and so on. And by the way, you're going to see it has its own blocks, so it's kind of, in some places, it has a little bit similarity to the function block diagrams. So, what are the components of a ladder? Why do we call it ladder in the first place? What are the components of it? So when you do create a ladder logic, you're going to see something similar to here. You're going to see two rails, two vertical lines, which we call them rails, and they are corresponding to the high power voltage and the low power voltage. So for instance, this could be like the ground, right? Like the 0 volt DC, and this could be the high power volt, maybe 24 volt DC. Correct? So they represent the high and the low voltage. They are called rails. And then connecting these rails are these basically wires, this connection, which we call the rungs. So rungs are connections that involve sensors and actuators. You typically see the sensors on the left side and the actuators on the right side. We talk more about it. And the goal of these rungs is to implement logical conditions, okay? So ifs and stuff like that. So as you can see, you have these vertical lines and a bunch of horizontal lines. That's why it looks like a ladder. That's why we call it ladder logic, of course. Okay, so it's quite a bit simple in terms of why we call it ladder logic. It's very easy to understand. Now, let's go back on and talk about the components. So we talked about the rails, right? The vertical lines, we call them rails. And there are two of them, as I said, one for high voltage, one for low voltage. The voltage typically, because the high voltage is on the left side, so you go from left to right. The logic runs from left to right. The rungs, that are the horizontal lines, okay, each one of them is numbered and they are going from top to bottom in a system of ladder logic. Then we have inputs in the system that are typically on the left side of the rung, and they are corresponding to sensors like or inputs like a push button that can be 0 or 1, or high voltage, low voltage, or a limit switch or stuff like that. Okay, or like a liquid level sensor, anything like that, a temperature sensor. So typically, as I showed you in the first video, they are directly connected to the input terminals of a PLC. And these inputs, some of them, we'll talk more about it, call them normally open or normally closed. So what is that? So if a switch, here we are talking about switches, if a switch is normally open, or NO, what is it that makes it separate from the normally closed? Of course, as the name says, the switch by default is open. When basically you energize the switch, or maybe mechanically push the switch, correct? Then you are going to close the switch. So you go from open to close. But by default, it's open. You have to press it to make it closed. Many of the push buttons are like that. On the other hand, we have some switches that by default, they are closed. You have to apply some voltage, force, or something, torque, to make them open. So by default, they are open, they are closed, but you can force them to be open, okay? So they are normally open and normally closed depending on what is their default situation. And in PLC diagrams, as we'll see later in Siemens, if the wires in a rung are all black like this, that means they are not energized. When you do the simulations, when they are energized, they go green like that. So if you see a wire, as we'll see in the future videos, if a wire or components attached to the wire go from black to green, that means they are energized, okay? And we're gonna talk more about it. The outputs, they resemble the relays, okay? And these are the ones that are connected to physical actuators, like what? Like an electric motor or a solenoid valve or a light or anything, correct? So whether the voltage, the energy is sent to that actuator or not, or indicator, that is an output. And we show them like these parentheses as opposed to inputs that are like shown like a capacitor or something. Okay, and they're also hardwired to PLC output terminals, so they can either be an analog output or a digital output. Good. When are they 1? When are they 0? They are 1 if the logic condition ending at them is a 1. So what does that mean? Let's read this. When I see some ladder logic symbols, that's the simplest thing you can get, like this, what does it mean? It means if input A, whatever input it is from any switch, let's say, if this is equal to 1, if it's energized, which means it goes close, then also set the output, whatever it is, Y or whatever it is, set that also to 1. So you see, it's an if statement. If input is 1 or energized or closed, then set output to 1. If the switch is pressed, then turn the motor on, right? So this is very, very simple. As long as the condition that ends up right before here is a 1, is a logical 1, then that output goes to 1. Good. So logic expressions are created using the combinations of inputs and outputs, as I'm about to show you. Now, many variables and inputs and outputs, they have their own memory addresses and they have their tag names, as well as there are some variables that are not necessarily input and output, like a time or a set temperature or something. So there are three major types of variables that you see in a ladder diagram. The inputs that are typically named by I and a number, like I, for instance, 1.0 or something, or 0.0 or 2.0. These are the inputs to the system. We have outputs, which are shown by letter Q, not O. So it's like Q, for instance, 2.0, that is like output 2. And then there are some memory variables that are not inputs and outputs, as I said, like a set temperature, set time, and something, and they are shown with M. So it might be M number 3 or something. Okay, sorry for my bad handwriting. So these are the three types of major variables that you see in diagrams. And as we go through examples, you're going to see, but let me show you just. So here, look, this is input I01. and then we have memory variable, and then we have output variables. So these are very common, and the name tags for those variables. So you know that, for instance, I04 is the low-level switch in a physical system. Okay, so there are name tags, and basically, as we just talked about it, notations to distinguish variables from each other. And of course, we can add comments as well. Comments, when you create these ladder networks, comments are typically added to the rungs on their left side and the first line of a rung. So if a rung has more than one line, have ors or stuff like that. So you see this rung here, this is one line of it, this is another branch of it. Typically the comments are added to this line, not this branch, and they are added on this top left side, as you can see here. So here on the top of this, you can add any comment that you want to explain the logic. Okay, so now that we know a little bit about some of the symbols that are used for inputs, outputs, where the comments go, the notations and name tags and so on, let's get more into what kind of symbols are common in ladder logic. And before that, one more time, let me remind you that the ladder logic is read from left to right, just like English, from the high voltage rail to the low one, and from left of the rung to the right of the rung, and from the top one to the bottom one, okay, from first to last. Now, how do we do logic with these symbols? And, which is and or, which is the most common types of logic, they are very easy. And this is very similar to electric circuits. And of two inputs is simply putting them in series. If you put them in series, then that is and between them. So this is literally A and then and B, okay? Because if the first one is like an open switch, it doesn't matter whether the second one is open or not. The result is always that wire, that circuit is open. The same thing goes for B. So in order for any electric voltage to pass through or electric current to pass through, both of these have to be closed or they have to be one. So you see clearly it's and. Series connection is and. On the other hand, or is parallel connection. So parallel connection is or, because if I want to pass current from this point to this point, all I need is either A or B to be open. Then it either goes through this top branch or this bottom branch. So parallel is or. Now, you might say, what is this guy here? Isn't that interesting? I have or between A and B. Not B, actually, between A and output, and the not of B is attached, for instance. What is this? But here we don't care too much about B. What we care about is this portion of it. This portion. This portion is what we call a latch, a latching circuit. What is latch? If you know a little bit about electric circuits, you know a latch is kind of preserving the last output of the system. What does that mean? Well, let's here assume that A and B are two switches, where A is the on switch and B is the off switch. Okay? Now, what's going to happen? And let's say, for instance, the output is a motor. So you have a motor and you have two switches, on and off. What do you want to do? If I press on and off is not pressed, what do you expect the motor to do? You expect it to be running, correct? And this is what you can see here. When on is pressed and on is A, this becomes closed. B is not pressed and is normally closed by itself, so without being pressed, this guy is already closed. Because of that, these two are closed, so the voltage passes through, and because this is AND between two ones in this path, this one becomes a 1, so this one goes on. Okay, the motor will turn on. Now what happens? When that motor turns on, we try to take an input from that output of the motor. We take an input that mirrors or mimics that output and put it in an OR connection with input A, which is the turn on button. What does that do? Well, if I go ahead and press on this on button one more time, correct? Press it one more time. What do you expect to happen? Because this, 1 second before I go there, since this one is on, since the output is on, now this input also becomes on. Okay? Yes, because this one is on. Now, as I said, if you press on the on button one more time, what do you want the motor to do? Well, it's the on button. It's not supposed to, whether you press it one more times or two more times or 10 more times. You do not want, by pressing more on the on button, if somebody by mistake presses on the on button, you don't want the motor to turn off. You want pressing on to have no effect on running the motor whatsoever. Okay? It's only the off button that if you press it should turn the motor off. Pressing more on the on button should not do anything. Okay, so how do you do that? You put that on in a parallel with this input that is mimicking the output. So now if I press on this on one more time, that goes back to open. So now what happens is this guy becomes open. Good? Well, what happens if that guy becomes open? This path is going to be a no-go for the electric current, but now this bottom path is already open. So the electricity goes like this. This path becomes AND between this output variable and input B, and this one still receives a 1 and stays on. Do you see that? So it keeps looking at the previous value of it, and as long as this is on, once you pressed on the input A once, the on button, pressing more on it will have no effect because this path is always open. So when would you stop the motor? That's where you press on this off button. When you press on this, since this is normally closed, it becomes normally open now. This guy becomes normally open. And even if this is normally closed, guess what? Because this is open, regardless of what A is and what output is, the electricity will stop here. So this guy goes to 0, then this guy goes to 0. So now the only way to turn the motor back on is to press on the off one more time to make it normally closed, and press on one more time to make it closed, and then you can run it again. Okay? So to keep the memory of the system, these latching circuits are very, very useful and very common, and we need to know about that. So this is AND, OR, and latch. What about the other gates of logic, like NAND, NOR, and XOR, which are very common? So for NAND, remember NAND means what? Means not AND. So this is not of A and B. And based on the De Morgan laws, if you know, that means not of A, if you remember, and then or what? Not of B. So if you have not of A and not of B and you OR them, that's the same as a NAND. And this is exactly what you can see. This is a not of A, this is a not of B, and they are ORed, they are paralleled. So this is a NAND circuit. Now you might say, does it mean that A is here normally closed? What is that? How does this become a not of A? That's exactly what it is. A normally, as we said earlier, a normally closed is considered a logic NOT. Why? Because here, look, if you look at normally open, if you energize it, it goes to 1. So energy means 1, and that is what you expect anything to work, that when you energize it, it goes on. But if you look at normally closed, when you give it energy, what happens? it goes off. It goes to 0. So you see, a normally closed is the knot of a normally open. So when you put this, it's like putting a knot on that, and that is exactly what we are doing here. So this is knot of A, this is knot of B, and they are OR together, so that is a NAND circuit. So what happens in this case? In this case, this light, which is the output, will only turn on when not A and B. What does that mean? It means when both of these guys are 0, if both of them are 0, not AND of that becomes 0, then not of that becomes 1. Also, if this one is a 1, this one is a 0, again the AND is 0, the not of that is a 1, and if this one is a 0, this one is a 1, the AND of that again is 1. So the only scenario that the light will not turn on is if both of the switches are energized. If both of the switches are energized, what's happening? Because they are normally closed, when you energize them, they become normally open. And now both paths to the lamp or the lights are closed, so it's not going to go on, right? That's a NAND. NOR, as I said, NOR means what? Means not or. So it's not A or B, which is basically, again, based on the De Morgan law, it's not A and then and not B. So you need not A, not B, and and means series, and that's exactly it is. So in this case, it's a NOR. Under what condition here this light will not turn on? Well, just all you need is one of these guys to be off, or both of them, or on. Sorry, if both of these are on or one of them is on, the series circuit will break, so it will not turn. So in this case, none of these two should be energized for the light to be basically on. None of them should be pressed. And then we have XOR, the most interesting one. XOR is what? Look at this. If you want to write it in logic, this is a not A and B. This is A and not B, and they are OR together. So it's this one or this one, and that is exactly the definition of XOR. Not A and B, or not A and not B. That is XOR. In this case, if you want the light to turn on, only one of them should be on. Only one of them, like A. If A is on, B is off, what's going to happen? Well, A is on, that means A is going to be open, because A is on. Well, actually, the other one is open. So if A is on, if A is energized, this is normally open. So that goes closed. This one is normally closed. That goes open. So that is A1. Now B off means B off means this one stays open. This is off, so this stays closed. And so this path is accessible to the light. That was when A was 1 and B was 0. Now we can look at the other scenario. This time let's make A 0, B 1. See what happens. A of 0 means don't energize A. So what's going to happen? A is not going to change. So A stays the same as it is right now. B, make it 1. So B is going to go the opposite. So this one becomes closed. This one becomes open. So this path is closed, but this path is accessible. Okay? Very well. Now, if you make both of them 0, what's going to happen? In this case, it should not work, right? Does it? Well, if both of them are not turned on, that's just as it is right now. This one is closed. This one is closed. It's not going. On the other hand, if you make both of them 1, then both of them will be energized. Both of them will be the opposite of what they are right now. So this becomes open. This becomes closed. This becomes closed. This becomes open. Again, you have 2 opens on each path, so it's not going to work. You see? So it only works when only one of them is a 1, and that is exactly the definition of XOR. Okay, so these are some common logics in a ladder logic. Now, Before we go to more symbols and so on, one thing I want to mention is PLC executes the programs in a cycle. So continuously it goes and checks on these inputs and reads their values. Are they still on? Are they off? Did the user change anything? They look at everything. And so if they are on in this cycle, it doesn't mean they will be on in the next cycle. Okay? Or if they are very slow changing, but the processing cycle of the PLC is fast, then before any of them changes, PLC can go through several cycles. Okay, so the speed of the PLC processing the code and the ladder logic is not the same as the speed of the sensors or actuators going on to off or off to on or anything. So we have to pay attention to that. And if we want so many cycles of the PLC to be the base of time for something, that's a separate story, and we have to count the speed of the sensors and the actuators. And we'll get to that when we go to more advanced topics. So if we want to look at the ladder logic symbols, we'll learn the normally open, the normally closed, and the output coils. There are other things that we need to know. Let's first go through the easy ones, and then we go back to the ones that need more time. So here you can do a logic condition and operational condition. So here you check whether A is less than or equal B, or A is bigger than or equal B, or if A is equal to B, right? Then you can add A and B, you can subtract A and B, multiply and divide, okay? So all of these are basically available in ladder logic. It's not just and or and so on. You can do operations, you can do arithmetic. You can do a PID controller. So if the input is error, the output is going to be KP times error plus KD times derivative of the error, and then plus KI times the integral of the error. Okay, so it's the output of a PID controller for an error input or something. Okay, so these blocks all available in ladder logic. Now let's talk about some other ones that are interesting. Now this is greater than or equal, so we know that one. So that is easy. So let's talk about these other ones that are a little bit maybe newer. One of them is called a set coil. Let's talk about the set coil, this one. So what is a set coil? A set coil is an output that when it goes from a 0 to 1, so if in the last cycle it was a 0, now the condition leading to it becomes a 1 all of a sudden, that will set the coil. So that makes it a 1. And it stays on being 1 even if the input of it goes back to 0. It's not gonna go back to 0. Okay, so all this one needs is to receive a transition from 0 to 1 to be set, and then stays set and 1 for basically as much as maybe a time allows or something. So this is a set. So it's kind of similar to that latch thing, if you remember. On the other hand, we have a reset coil. Here, this one is again expecting going from 0 to 1. So it was 0. Now, as soon as you make it a 1, instead of energizing the output coil and setting it, it forces it to go to 0. It resets it to off. Okay? And even if the input to it goes back to 0, it's not going to affect this resetting. It is going to be resetted. It's going to be open. Okay, so these are two basically similar to a latch, one of them for priority for set, one of them for priority for reset. And after they are set or reset, they don't look at the input anymore. They don't care about it anymore. There is one that is called one-shot positive edge. You see a P inside it. What is this one? Now, when the input goes from 0 to 1, so you see a positive edge going from 0 voltage, let's say, to 1 or 5 volts or whatever you call 1. Then the output goes 1, but not forever like this. Or I mean, not they have reset mechanisms. So this set one has stuff for going back to reset, and this reset has stuff for going back to set. But all they stay on is for one PLC scan cycle. They go on and they stay on. Okay, so if this is the input to this, the output will be similar. The output will be set to on for one cycle, okay, and then goes back to 0. Now, this time of one cycle is different than the time of this input, okay? It depends on how fast your PLC is and how fast it is scanning the code. But for these, no. I mean, if it goes from 0 to 1, the output goes from 0 to 1 and it stays like that. Here is the opposite. When it goes from 0 to 1, okay, if it was a 1, it goes to 0 and stays there indefinitely. Okay? So we need to see the differences between this kind of relays or outputs. Now, the time is very important. Many times you care about time. You want an operation to only be done for so much of time. That's where you have timers or delays. And there is timers for on, and there is or timer or delay for off. So let's look at these. So one of them is called TON, timer delay on. The other one is called timer delay off, or TOFF. So what is this? This time on, when it receives a 1, the timer, the clock, starts ticking. So you see the clock starts ticking. From 0, it keeps counting until a preset time has been reached. Let's say 20 seconds. So when it receives a pulse, the clock starts ticking until so much time that you gave to it. Then after that 20 seconds is reached and passed, now it turns the output on. Yes, so you see, it's not like, hey, I received an input pulse of 1, let me go ahead and turn the output on as well. No, it's not going to do that immediately. It's not going to do it right away. So if this is the input and this is the output is not going to go to 1 immediately like input. It waits some time. So it waits after this some extra time, then it goes on. And this extra time from here to here, that is that 20 seconds of delay for turning it on. Okay? Now, after this 20 seconds, it turns on, and when it turns on, before it turning it on, it also looks at the input situation. If the input, when it starts turning it on after 20 seconds, it looks at the input. If the input is already back to off, it is not going to even bother turning it on because the input is off. But if the input was on, after it was initially set to 1 and it was kept as 1, now after 20 seconds, it also turns the output on. So it's not just the 20 seconds that determines the turning on or off of the output. It's whether the input is still on or it went back to off. Okay, so this is something very important to look at. There is a similar thing for this off one. Here, again, it looks at the input. If it goes from 0 to 1, okay, so immediately turns the output to 1, to on, or 1. And then does not turn the output off until so much time is passed. So let me show you in graphics. So let's say this is the input. It goes 1 right now. and the output was 0, as soon as it receives the 1 from this, it goes on as well. Now, for how long? As soon as this output goes on, a clock starts ticking. And when these clocks reach the preset time, let's say 30 seconds, so after 30 seconds being on, now it will, it tries to turn it back to off. Okay? Now, it will turn it off after 30 seconds if the output at that time, at that 30 seconds, is also at 0. So if the input was off and 30 seconds passed, now it is time to turn the output off. But if it looks at the input and it says, oh, look, the input is still on, it never turned off, this is not going to do that, and immediately it turns it back on, so it keeps going continuously. So this one delays turning off the output, this one delays turning on the output, but at the same time, they look at the input to see whether the input is agreeing with that or not. Okay? So these are the timers, and these are very important, and we're going to get to them. The other thing is, sometimes it's not the time that matters, it's basically the number of cycles that matter, a counting operation, not just time in seconds. That's where we use the counter up and the counter down, CTU and CTD blocks. So what does CTU do? It looks at the input to go from false to true, then it starts counting. One at a time, going up from 0, so it starts at 0, and each cycle it keeps adding a number to the counter. So it has a counter, and as soon as the input goes from 0 to 1, it starts counting each cycle. Until what? Until a preset number. So let's say the preset number is, for instance, like what? 10. So when 10 is reached, 10 cycles, then what? Then the output will go through. So the output does not go through immediately. It goes through after so many counts. So this from here to here is not 10 seconds. This is 10 cycles. And the cycles could be like in milliseconds, so this could be way shorter than 1 second. And what happens to this counter variable that is now up all the way to 10? Would it stay at 10? No, it goes back to 0. So this one is going to be reset back to 0. And then there is the opposite of that, counter down. Again, where this one receives a 1, so the input goes from 0 to 1, it has a counter value, but the counter value does not start at 0. For this, it starts at the preset value. Okay? So it starts at 10, and then it goes down one at a time. So next cycle goes 9, 8, and so on. Okay? And that is when, after those many cycles passed, 10 cycles, again, that is when the output goes on. So again, this is going to be 10 cycles. And what happens to the counter? Because let's say it went all the way down to 0. What happens to it after this 10 cycle and the output goes to on? What happens to this? Well, guess what? It goes back to 10 again, and be ready for the next set. So basically, these two are for loops. This one is for I goes, let's say, 1 to 10, let's say, and this one is for I equals 10 with increment of -1 going down to 1. Yes, this is a backwards for. And these are also fours, but these are for time, not for counter. Okay, so these are some of the very common blocks that you see in ladder logic, and there are some other symbols that you might see. So let me briefly talk about them. So you might see, if you see this symbol which I showed you earlier, that's a light, an indicator lamp. If you see this motor with 3 lines in it, it's a 3-phase motor. If you see the one like this that has only 2 wires, that's a 2-phase motor. Then you might see the basically normally open and normally close with this kind of symbols. Okay, instead of this one and this one, this one, you might see them like that. Okay, if there is a heating element, you might see it with something like this. So if you see that, that's not a PWM or pulse or something, it's a heating element. If you see a solenoid coil, you might see this kind of sawtooth signal. If you see a fuse, it might look like this, and an overload heater is something like that. Okay, so these are some common other symbols that you might see. Now that we have seen these, let's talk about a few examples. Let's look into a few examples. So if I give you something very simple like this, and I say, what does this ladder logic do here? What would you say? Say, well, look, here I have a normally open start button, and I have a normally closed stop button. Okay? The motor output is also corresponding to a normally open variable in the input. So this is the symbol of a latch. As you remember, this is a latching circuit. And when this variable is on, if it goes on, then the light will turn on. So that is very simple. That means I have a start switch that is already closed, that is already open, but as soon as I press it down and it goes normally closed, this becomes a 1. This is already a 1. So this path here will be open. So the motor will go on. And when the motor goes on, this one stays 1. So now even if I press on this start button again and make it go open, who cares? This path is on. Look, this path stays on until I press this one. Then it will go off. But pressing the start button one more time is not going to affect anything. All it needs is one press. The motor will go on, and as long as the motor is on, guess what? The light will stay on. So that's all it is. Turning a motor on with an on button by pressing it one time, a light will show. As long as the motor is on, the light will show that it is on. When you press on the stop button, then both motor and light will go off. Pressing the on button one more time is not going to affect anything. Okay, so that is very, very simple ladder logic. Now let's look at a little bit more advanced example. So this time you're looking at a tank. Again, these examples are coming from the website I just mentioned. I did not make them. So here you have a tank. The material is going to come in through an inlet valve, and it has 2 sensors, a low level and a high level. It also had heaters and a temperature sensor. And the tank has an outlet valve for discharge in it. So what is it that you want to do in here? The operation, the logic for this is like that. Basically, if the system detects a low level, so when this one starts filling, and this one is a normally closed thing, so or normally open, so this one does not allow anything going on. When this one opens and this fluid starts going up, or if it is on, as soon as this low level sensor is actuated, that means there is not enough of that liquid or whatever it is, solution inside the tank, the system should start feeding the tank. So you might say, well, didn't you just say this one was turned on? Well, not necessarily. So let's say the tank was on to begin with. So the tank was filled all the way up here. And we open this, and it is going down, 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 down. As soon as it reaches this level, this one will turn on. And that means, hey, you are now very low. Go ahead and close this guy. Don't let it run. Instead, open this one. Okay? So when this low-level sensor is actuated, the system should start opening this and allowing the liquid to go in. Then, when it is filled all the way to the top and this one is actuated, this one should go open again. When that one shows that it is filled, now you have to stop feeding, as we said, and start the heating process. So now you're going to energize this when it's filled and start heating it until a set temperature. So let's say it is coming in at 20 Celsius, and you have to keep heating it until it goes to 50 Celsius. Then you are going to let it go. Okay, so that is a very simple logic. Opening, closing valves, sensing temperature, turning on and off the heater. That's all it is. Okay, so it's a heating tank. That's all it is. And the temperature sensor could be a thermocouple. It could be a resistance temperature sensor, or RTD, right? It's a sensor that its resistance changes with temperature, correct? You might call it a thermistor. And so what are the variables? What are the input outputs? If there is a memory or anything, what are the things that are involved? Let's give them some name tags and some variable names. So we write a more professional looking ladder diagram as opposed to something like this. So here we first identify the inputs to the system. Clearly the inputs to the system are what? Clearly there is a stop button here, which is not shown in this picture, but there is a control panel, probably right here next to it. There is an on button, or start button, let's call it. When you start it, the system should start operating. There is another button that is the stop button. When you press it, the system should stop. And of course, the low level switch and the high level switch. These are the inputs to the system. And we are going to name them by variables I00, 01, 03, and 04. What about 02? Well, you can give it, they don't have to be all exactly in a specific order. So you can give them any name that you want. If you don't like it, call it I02. So start button 01, 00, stop button 01, low level switch 04, high level switch 03. Okay? This is what it is. What are the outputs? What are the things that you are trying to control? Where is clearly the heater and the inlet and the outlet valves. These are the things, these are the actuators of the system. You're trying to control those. So the inlet valve, we call it Q0. The heater is Q1 and the outlet is Q2. So this is Q02. This is Q01. And this guy is Q00. Okay, so these are the inputs and the outputs of the system. And what else? Well, here, one of the things you can do is actually this temperature in the system could be another input, really. That actual temperature here is considered a variable, a memory variable, but actually, and this is coming from the website, I would rather bring it as an input to the system and say actual temperature is another input, call it I02 or something. Now, what are the things that are basically not sensed? The major one is the set temperature, that 50 degrees that we mentioned. That set temperature is the kind of variable that you have to hard code into the system and there is this master coil. It's not super critical, we'll talk about it. It's kind of like a cycle, whether the cycle is on or a cycle is off. Okay, so we'll talk about this. So what are we doing here? Let's look at the ladder logic and the network of it. So here, this is how we do it. Network 1, okay, this first thing that you do. Let's read this. It says if the stop button is not energized, so nobody pressed on the stop button, but the start button is pressed. If the start button pressed, this one becomes closed. That means this path will be available for the current to go. When that path is available, the master coil or the cycle on will turn on. And when that turns on, this variable that is mimicking that will go on and allows this path basically to be on for as long as this stop button is not pressed. So that is a latch. As you can see, this is clearly a latch. Which means, hey, as long as the stop button is not pressed and the start button is pressed once, let's keep running. Let's keep going. When the stop button is pressed, then we're going to stop the master coil and the whole system. Now what? Let's look at the logic of the system. So it says, if the master coil is on, the system is running. Now, how would you open, when would you open the inlet valve? Remember, the condition we need for opening the inlet valve is when this low level sensor is activated, when we know that we don't have enough in the tank. So here we add this low level sensor, the low level switch, and we put it in series with the master coil. So as long as the system is running and this low level sensor becomes activated, it senses low level of liquid in the tank. Guess what? The high level switch is normally closed here. So that is always one. As long as the low level is on, this path becomes available. Let me use the green color to mimic the same thing I said when it's energized, this one. So this path becomes available. That means the inlet valve goes to a 1. And again, you see a latch for it here. So the inlet valve will stay on as long as the low level sensor is activated. And as long as what? The stop button. Now here you see the stop button, the start button is not really playing any role because what? Because this path is available. So the inlet valve stays open. For how long? For as long as this low level switch is on, or this guy here, look, these are all, one of them will work. It's this guy that determines everything. It's this one. When the high level switch is activated, this one becomes open. So now it doesn't matter what was the previous history of the inlet valve or whether the low level switch is on or off. As long as the high level switch becomes activated, hey, your tank is full. Go ahead and shut this off. And so this one goes off. Okay? So you see, it starts when the low level switch is activated here and stops when the high level switch becomes activated. And that is exactly what you expect it to work. Now what? So that was the control of the inlet valve based on these two switches. Now the two other things we have to write logic for them. One is when to turn on and off the heater. The other one when to turn on and off the output valve, right? So you need to write logics to go from these inputs to what? To these outputs. Based on, of course, also some other set variables that you have. So going from these set variables and inputs to the outputs, this is the part that you write the logic for. And since there are several outputs, several actuators, you need several networks. One is just to run the system. One is for the inlet valve, one for the heater, one for the outlet valve. Okay, so it's clear why we are writing it this way and how many we need. Now let's look at the network number 3. Network number 3 says as long as the system is running. Now let's look at the high level switch. When the high level switch is reached, which means the tank is full, now the outlet valve is normally closed. Okay, it's normally closed, so this path becomes available, which means go ahead and turn the heater on. And when the heater is on, the latch for it becomes active. So now even if this high level switch becomes de-energized and the liquid is going a little bit down or not going down or anything, because there is a latch, there is a parallel path, so the heater will start. So now the heater don't look at the high level switch whether it's on or not on. It doesn't care anymore. As soon as you turn it on, it doesn't look at the high level switch anymore. The only thing that is affected by is this guy, outlet valve. It looks at the outlet valve. Is the outlet valve energized or not energized? If it's not energized, means it's not open, means the signal is not sent to it, because it's normally closed actually. So when it's not energized, okay, when it has not opened for the liquid to go out, keep heating. But whenever this outlet valve becomes energized, the system send the signal to it to open and let the fluid go ahead and turn the heater off, because this is time for discharge. You don't want the heater to be on a tank that is discharging. Turn the heater off, let it do the discharge job. Okay? Finally, how would you control the outlet valve? What would you do for the outlet valve? When would you know it's time to open the outlet valve? As we said, it's only when the temperature T that you sense is reaching the set temperature. When the actual temperature measured is reaching the set temperature, that is time to open this. So let's look at this one. Let's look at the logic again. So when the system is running, and when the actual temperature is what? Bigger than or equal set temperature. This variable is bigger than or equal this variable. You see here the operator, the operational block basically. When T is bigger than T set or equal, go ahead and, hey, the temperature is reached. Okay? So this one becomes a 1. The low level switch is already closed on this, so this path becomes available. When that path is available, the outlet valve becomes 1 and it stays 1. Here you see the latch for it. So now this path becomes on and it keeps discharging. Regardless of now the temperature that the thermostat or the thermistor is measuring, because during the discharge the temperature can change. Now it doesn't care about it anymore. Once it reaches there, it opens the discharge valve and it doesn't look at the temperature anymore. It has no effect. Whatever it is, whether it's bigger than or equal set, or because of the discharge the temperature dropped a little bit, it doesn't care anymore. It keeps discharging until the low level switch is energized. When it goes down and when the tank is almost empty, this one becomes energized again. Since this is a normally closed here, energizing it, make it a normally open, and normally open means, hey, go ahead and turn the outlet valve off. When the outlet valve is off, guess what happens? When the outlet valve is off, here, this one is being affected by it, the heater system. The heater system looks at the low level switch, okay, and the outlet valve. So hopefully you can see how this ladder logic is controlling the heating of the liquid and the system. Now let's go to the last example, which is even more complicated. And here you have two liquids coming in, A and B, and the system has a motor that will mix them. You have a low-level liquid sensor. You have a liquid sensor for A, which is coming first into the tank, and then once A is filling up to this level, then B starts coming in, and B should reach to this level for allowing the system to start mixing. Okay, so here, as we said, when the low level is sensed, material A, this one opens, material A starts coming in until this level is reached. When this one is reached, then this one becomes open, B comes and fills, so B is going to take this part, A is going to take this part. When this one is sensed, then both of them will go off. Now the motor starts going on, and it goes on for so much of time. Okay, it goes on for so much of time, which I guess in this example was something like 20 seconds or so. So it mixes A and B for 20 seconds, and that is when it is allowing for the outlet discharge valve to let the mixture go out. Another element, there are two other outputs in this system. One is a cycle on. This is like that master coil thing, a light that will show whether the system is on or off, and that is determined by this start and stop button. And there is also a buzzer. Okay, so there is a buzzer here. When the mixing process is completed, when this motor goes on for 20 seconds and the mixing is done, then the buzzer will go on for 5 seconds, and then it will go off. Okay, so when the mixing is done, the motor turns off, the buzzer will give a signal to people for 5 seconds. Hey, be ready, the outlet valve is going to open and the liquid is going to be dispensed. Okay, so here you have more outputs and you have more inputs. So if you want to talk about inputs and outputs, the input is the start button and the stop button, the low level switch, the high level, the level for material A and the level for material B. And the outputs are the light for cycle on, the control of the inlet valve for A, inlet valve for B, the motor, the outlet or discharge valve, and the buzzer, right? So you have 5 inputs and 6 outputs. And of course, since you have 6 outputs, you clearly need at least 6 networks to control everything, okay? So this is how you want to write the logic with a bunch of networks. And here you see that there are 9 networks. Why? We're going to talk about it. But this is the summary of what we need to do. So network 1 is very similar to last time. If the start button is pressed, because the stop is normally closed, this path becomes active. That means the light for cycle on becomes 1. So that light turns on, and it's a latch, so it will stay on now regardless of whether you press that start button again or not. It will only go off when the stop button is pressed. Okay, so that is the first thing. A light indicating whether the system is going through the cycle or not. That's the first thing, the light circle. Now, as long as the system is running, this is a 1. Now what? Now you look at the low-level sensor, the very bottom sensor, which determines that there is almost nothing in the tank and you have to start pouring in liquid A or material A. Okay, so what would you do? The first thing is that sensor should be activated, so it should receive a 1. When that receives a 1, here you see that this level material A is used as a normally closed, so this path is available. So the inlet valve 1, which is for material A, that becomes a 1, and there is a latch for it here, so it keeps pouring A in regardless of whether you press the start button or not, and whether this low-level switch is turned on or off or not. When that one becomes activated once, that's enough for A to keep pouring in. Until what? Until A sensor is activated, which means, hey, you have enough of A. Now the tank is filled all the way to here. Go ahead and stop tank inlet valve 1 or A. So that is when this one becomes open, this one goes off. Then what? Let's look at the next one. In the next one, you can see that when the cycle is on and when sensor for level A is on, since B is normally closed, this path becomes available that starts the inlet valve B and there is a latch for it. So now it is not going to look at sensor level A anymore. It doesn't care about it because this path is available. The only reason that the inlet valve 2 for B, this one, the only reason for this to go close is when this sensor says, hey, you got enough, you got now to the level for B, go ahead and stop it, and you can see that here. When that sensor is activated, since it's normally closed, it goes normally open. Now this is going to stop. Okay, so you see level by level, it's filled from low level to A, from A to B. The valves, inlet valve for 1 and 2 or A and B opened. Now they are closed. Now we go to the next part of the cycle. The cycle is still on. Material level B reached, which means the tank is full now. Now it looks at the timer. The timer is automatically closed in the beginning. So what's going to happen? The motor starts. So as soon as tank is full, the motor is going to start, and there is a latch here, so the motor will keep going. Until what? Until this timer is energized. When this timer is energized, this guy goes open, the motor will stop. Now, what is the condition for this timer to be energized or to go to 1? When does the output of the timer go to 1? Here, the next network will tell us everything about that timer. So this timer Q is exactly what you have down here. Let's see what it is. So this cycle should be on, otherwise that timer doesn't work. And the motor should be on. So if the motor for any reason fails and it goes off with any electric shock or anything, this system breaks, the timer stops. But if the motor is on, is spinning, and the light is on, nobody pressed the off button, right, or stop button, this timer keeps counting time. This is a timer on. Okay? And initially, remember, if we talked about timer on, they have a delay in turning the output on. So in the beginning, the output of it is 0. But after this PT means preset time, after T of 20 seconds, right, this guy jumps to on. Okay, so if initially it got a trick to start, after 20 seconds, the output of it will go on. The output will go to Q. And when this Q, which is here, you see timer.Q. The Q, the output of the timer, when that one goes on, since this is normally closed, it becomes normally open, which means turn the motor off. And when the motor is off, guess what? This one is normally open, so the timer is not going to work. So the timer, first of all, will only work when the motor is on, and it only will count 20 seconds and then shuts the system down. So in is the input to this timer, on delay, Q is the output of it, which is used right here. PT is the preset time, which is 20 seconds, and ET, which we don't use, that is elapsed time. In some applications, you need to keep track of the elapsed time, and in this case we don't, so we don't really need to care about this. But many of the blocks, they have ET or elapsed time that you might need to use somewhere. So you see these two networks 4 and 5 work together. There is communication between them. This one goes here, that one goes there. There is internal working between them. Good. So 20 seconds passed. The motor is turned on by the off by the timer, right? Because the timer is normally closed here, so the motor goes off. Now what happens? This is the time that the mixing is complete. You need to open the discharge valve. So let's look at here. Now the cycle is still on. The timer.q, you see the timer.q is normally open here. Up there it was normally closed. That's another thing you have to keep in mind, that you should not necessarily use the same kind of variable in all over the place. So if the timer.q use a normally close of it here, you can here use a normally open of it. They don't have to be the same thing. Okay? So as I said, after 20 seconds, this one goes to a 1. So this one becomes energized. That is closed. The cycle is closed. The low level sensor, you see you are using a normally closed version of it. Look up here. If you look up here, use a normally open of it. Oh, I'm sorry. Look. So again, you can use different versions of each input in different places. This one is normally closed. This is all going to be closed. So what's going to happen? The outlet is going to be energized and the latch is going to stay on. So that means now the outlet will keep running and discharging, and it doesn't care about the timer anymore. The only thing it looks is the bottom low level. When the bottom low level is reached again and the tank is empty, this one is energized, that goes open, this one stops. So this charge keeps going until the tank is empty. Good. Now let's look at the buzzer. What happens to the buzzer? For the buzzer, first thing first is you need to make sure the cycle is still on and the timer Q is on, so the timer should be energized. It will do a set on the buzzer. Okay, so first of all, 20 seconds should have passed, which means the motor did its job and stopped for this to go on. After 20 seconds and the motor operation, now the buzzer signal will be set. So now after 20 seconds of motor working, now the buzzer will go on. That is the buzzer. Then what? It sets the buzzer to 1. So now this guy is going to be a 1. And now you see buzzer has its own timer. Remember, we said when the motor is on, the buzzer should go on for 5 seconds. So you see it has its own delay for 5 seconds. So when that 20 seconds pass, nothing happens. This one becomes on. Now it keeps ticking for 5 seconds. After 5 seconds, now it goes on. Okay, so this is that input to it. This is the output of it, which goes on. And this is that 5 seconds. Now, after 5 seconds, it's the time to send the signal of the buzzer reset timer Q. Okay, it's time to send the signal to 1. Now, when that becomes 1, which is right here, this becomes a 1. When that guy goes to 1, what's going to happen? The buzzer is going to go to reset. And remember, this is connected to the buzzer actuator, the buzzer speaker. So when it's set, the buzzer is buzzing. When it's reset, the buzzer is going to basically go quiet. Okay, so it waits for 5 seconds. Initially, it turns on. After the motor is turned off, it turns on. Keeps going on for 5 seconds. After 5 seconds, it is going to be reset to 0 and the buzzer will shut down. So hopefully with this lecture, you learned some basics about ladder logic, how the ladder logic is working, going through examples and everything. And once in the next lecture, which is about function block diagrams, I'll show you the stuff in Microsoft OneNote. In upcoming videos, we're going to do similar projects to these, but we are going to do it in Siemens Simatec PLC simulator. So first we're going to do it software. I show you how to create stuff like this in Simatec software. And then later, when I show you how to set up the hardware of the Siemens S7 1200 PLC, we're going to connect the software to hardware. We're going to download the PLC logic on it, and we're going to physically do the examples. Thank you so much, and see you in the next video.